So part 2 of our discussion in 16.7, we take up what I call the second type of integral. In this section, the double integral over a surface S of f dot ds. And let's just quickly set up again the context. We have a vector function going from the UV plane, say some region D, over here. And it gets us to a surface in the XYZ plane, or XYZ coordinate system. And maybe I will again try to draw sort of the same thing I had last time. So this being the surface S, I'll make it a little bit less messy. Okay, and I also want to draw a little bit of the vector field F. Let's see, I think I'll indicate that F is kind of going like this. Where some of these vectors of the vector field are behind the surface S. So I'll indicate that by dashing these a little bit. So the vector field's coming down on it from this side. Some of these vectors are on the other side of the surface, so you couldn't really see them. And then here they come out back again on this side. Okay, and the idea behind all of this is that we think of F as representing fluid flow. And think of S as a net, or a sort of net, if you will. In other words, S is something that has a definite shape and location in 3 dimensions, but it also allows a fluid to flow through it. That's the nice thing about thinking of S as a net. It allows us to talk about all of that. And we are going to say that the double integral of F dot ds is, as we said earlier, the double integral over D or actually still before we parameterize, double integral of F dot n ds. And what we're now thinking of is when we take the dot product of F with a vector which is normal to the surface. So So at any point on the surface, we've got a normal vector, and then we've got F. If the normal vector is pointing in this direction and the vector field is moving in this sort of the opposite direction, then this dot product will be negative, indicating that the normal vector is pointing outward, sort of normal here. So outward's not quite the right word. The normal vector points in this direction, but the vector field is moving from this side to the other side. So that would give us a negative dot product, indicating that the vector field is not flowing in this direction, it's flowing in the opposite direction. So I just, in those words that I said, I talked about, one side or the other side. Given the picture that I've drawn here, it makes sense to talk about this side or the other side. But there are surfaces for which it does not make sense to talk about which side. So we want to avoid those types of surfaces. So before I go any further with this talk of this dot product and a normal vector giving us a direction and possibly the vector field going possibly in that direction or in the opposite direction, let's first talk about surfaces a little bit. Any surface for which the choice of a normal vector determines a direction across the surface is said to be orientable. Let's go back and talk about this choice of a normal vector. Let me come maybe out here. At any point on this surface, there's a normal vector which goes, say, in one direction. In this case, kind of up and to the right. And then there's a normal vector which will go in the opposite direction, and that would be minus the normal vector which goes in this direction. So let me just draw for you, or actually show you. Here's a long, thin rectangular slip of paper. You can see it has two sides. It has a side with no writing on it, and it has a side that's got some writing on it. I'm actually going to change this a little bit, but I'm going to keep it as an orientable surface. I'm going to take it and I'm going to connect it at the ends and make it into more or less a band that if you had the right size wrist, you could maybe fit it over your wrist. So if we suppose it doesn't have this weird, suppose it actually connects nicely. This is still a two-sided surface. And I'm going to bring in a push pin here to represent the choice of a normal vector. So if I'm interested in the flow of a vector field from this side to this side, then having the push pin like so represents my choice of a normal vector. If I want to represent if I want to calculate the flow in the other direction, then that means I'm putting the push pin on the other side of the surface. And when I get F dot n positive, that means the vector field is flowing from this side through to this side. Now, this again is a case where it makes sense to talk about two sides, and let me show you why. If you put the normal vector on the surface, you can move it around, and as the normal vector goes all the way through the surface, changing continuously, never having to take like a big jump, that normal vector stays on that one side of the surface. See, it's always going to point outward. It's always going to point normal to the surface, and it's always staying on the outside. It might not even be clear why I would call it staying on the outside, because like, what's the alternative, right? Let me show you the alternative. Here is another slip of paper, which initially has two sides to it. As I start to make a band out of it, here's what I'm going to do. I'm going to take one of these ends and I'm going to flip it around. So instead of going like this, I take this end and I flip it and I go like this. And then I make the connection. And if I did it really nice, it wouldn't just be a staple. It would, actually merge, the two pieces. But this is good enough. Now imagine. You don't have to imagine it. I'll do it. The push pin. You say to yourself, okay, let's consider the flow of the vector field from this side through to this side. So this is my normal vector. But as I move that normal vector around the surface, just continuously transforming it, just moving it a little bit at a time, if I keep doing that, all of a sudden, I end up on what appears to be the other side of the surface. Now, that normal vector has never left the surface, but as it never left it, it ended up on the other side. So that little strip of paper I made, this is called a Mobius strip. Probably supposed to capitalize that because it's a guy's name. Is it capitalized in my notes? I'll never find it. A Mobius strip is non-orientable. It's one-sided is another. It initially looks like it's got two sides, but if you take those sides to be defined by the choice of a normal vector, you can move that normal vector all the way around, and at some point the normal vector ends up on the other side. Another way to say that is you can paint a Mobius strip. You can paint the whole strip and never take the paintbrush off of the strip. If I'm going to paint a band, I could paint the outside. I could keep moving it around, but in order to paint the inside, I have to take the brush off and reapply it to the inside. So there really are two different sides here. And because there's two sides, we can talk about flow this way, flow that way. Here, we cannot talk about that. So all of this to say, I enjoy talking about stuff like this. You don't have to stress out about it. we will avoid. In other words, we will not work with Mobius strips and the sort. So every surface that we work with will be orientable. In other words, the choice of a normal vector determines a direction across the surface. Okay. By the way, a Klein bottle is a four-dimensional version of a non-orientable surface. You may have heard of the Klein bottle. You cannot have a, it's an extra dimension. The Mobius strip starts off as two dimensionals, but of course we can see it in three dimensions. Go up an extra dimension and you want a non-orientable surface with that extra dimension, it's called a Klein bottle, or at least that's one such surface. Okay, so what do I want to say now? So let's go back and look at this. Here's our surface S. The surface is given by, and this is not very clear, R of UV. We've already seen how the vector function R of UV gives us a normal vector. For the surface S, RU cross RV is normal to S. And so we can take N equal to RU cross RV divided by the magnitude of RU cross RV. And that always gives us a normal vector in one direction. Minus N is the normal vector in the other direction. So then the double integral over S of F dot N ds is adding up all of the little f dot n's. In other words, it's adding up the component or components of F going through S in the direction determined by N. Add up all of those. This yields the total flow or flux of F across S in the direction. So these are called flux integrals, and flux is just the total flow of the vector field across the surface. So again, going back here, you can see if we choose these vectors in, which are going from what you might think of as the side away from the viewer, you know, from our perspective, towards this side and through this side out of the paper, then at some locations, F dot N will be negative, but keep, you know, N over here. Certainly over here, you know, we're getting F dot N to be positive. And so we would be adding up some negatives, adding up some positives, seeing what the quote unquote net effect is, and that would give us the net flux or flow of the vector field through the surface in the indicated direction. Okay, so let's see how to compute that. So the double integral over S F dot N ds is the double integral over S of F dot, and then we've already said what N is. N is R sub U cross R sub V divided by the magnitude RU cross RV. This is the differential of surface area we saw even in our just, you know, the very first part of our discussion, that the differential of surface area is magnitude of RU cross RV dA. So this is magnitude of RU cross RV times dA, where now we are, you know, this area here is the area back in the UV plane. Well, these cancel out, of course. And now we're back in, and I really should have D. I really should have D here as well. So this is the double integral over D. We're parameterizing everything now. So F is in terms of R of UV. And the only thing left over here is times the, or dot, not times, vectors here, dot RU cross RV dA. And you just, you know, as you saw in the last example from the previous section, you just have to look at D, see what it is. Do we need to go polar, rectangular, or something else? Let's see. There are some special cases. Let me just say that this gives us the flux. Of F across S. Let's see. So let's look at the special case where S is given by Z equal to G of XY. Okay, so not this case, but a case where Z on the surface is a function of X and Y. Then here we need a couple of things. We need the normal vector. Well, we saw in 16.6 that N equals minus Z sub X I minus Z sub Y J plus K is normal to S. go back, and if you don't recall that, I talk about it in the lecture. You can see this derived also in the book. Since K since the coefficient, I guess, of K is positive, we call this upward normal. So a normal vector to the surface, in this case, is given by this, because this leaves us with a positive multiplier for K here. We call this upward normal. Minus N, of course, is downward normal. And so then the double integral of f dot n ds becomes, in this case, the double integral over d of f dot minus z sub x minus z sub y 1 dA. If f is given by p, q, and r, then we get the double integral over d of p, q, r dot minus z sub x minus z sub y 1 dA, which is the double integral over d of, this would be minus p c sub x minus q c sub y plus r dA. This is at least what it is for upward orientation. For downwards, of course, you change the signs there. All right, I totally get it. This is a long, very theoretical discussion we've just had. We will back it up with some examples in the next 2 parts of the lecture.